On September 24, 2023, a capsule the size of a mini-fridge separated from a spacecraft 102,000 kilometers above Earth and fell through the atmosphere at 44,000 kilometers per hour. It hit the air hard enough to glow. Parachutes slowed it. It landed in the Utah desert at 8:52 in the morning, about 80 kilometers from Salt Lake City, in a restricted military test range that had been cleared for the recovery. Inside the capsule was 121.6 grams of material from the surface of an asteroid called Bennu, the largest sample ever returned from space by an American mission, and the most scientifically significant asteroid sample ever brought to Earth. The analysis teams who opened it found black dust, dark pebbles, and something that took months of careful laboratory work to fully characterize: organic molecules, amino acid precursors, and water-bearing minerals that are 4.5 billion years old. The asteroid those samples came from is currently on a trajectory that gives it a roughly 1 in 2,700 chance of striking Earth on September 24, 2182. The date of the sample return and the date of the potential impact share the same day of the year. That is a coincidence. What the samples are telling us about where Earth's water and organic chemistry came from is not. Bennu is a near-Earth asteroid about 500 meters in diameter, roughly the height of the Empire State Building. It is classified as a B-type carbonaceous asteroid, which means it is dark, carbon-rich, and chemically primitive. B-type asteroids are among the oldest objects in the solar system, preserving material from before the planets formed, from a time when the solar system was a disk of gas and dust, and none of the rocky bodies we know today existed yet. Bennu was selected as the OSIRIS-REx target from a list of over 500,000 known asteroids based on 3 criteria. It had to be accessible given the spacecraft's fuel budget, large enough to safely navigate around, and scientifically valuable. Carbon-rich asteroids like Bennu are thought to be remnants of the same type of material that contributed to Earth's early chemical inventory, including, possibly, the organic molecules and water that eventually made life possible. Bringing a sample back from Bennu was, in part, an attempt to test whether that idea is true. Bennu was discovered in 1999 and has been tracked continuously since then. Its orbit crosses Earth's, and over decades of tracking, gravitational and thermal modeling has refined its trajectory enough to calculate impact probabilities centuries in advance. The 2182 date is not a guess. It is the product of extremely precise orbital mechanics, refined by data from the OSIRIS-REx mission itself, which mapped Bennu's gravitational field in more detail than any asteroid has ever been characterized before. OSIRIS-REx launched in September 2016 and arrived at Bennu in December 2018, after a 2-year cruise that included 1 Earth gravity assist. The spacecraft spent the next 2 years in close proximity to the asteroid, mapping it with cameras, spectrometers, and a laser altimeter. The first surprise came immediately. Scientists expected Bennu's surface to be mostly smooth, a beach of fine-grained material based on thermal emission data from Earth-based observations. What the spacecraft found was a chaotic landscape of boulders, some the size of buildings, covering essentially every part of the surface. Finding a safe site for sample collection required over a year of searching, imaging, and analysis. The originally planned site was abandoned. The team eventually selected a small crater named Nightingale, about 16 meters across, in Bennu's northern hemisphere. The sample collection event, called Touch and Go, or TAG, happened on October 20th, 2020. The spacecraft descended from its safe observation orbit, extended a robotic arm called TAG-SAM, and made contact with the surface for approximately 6 seconds. TAG-SAM fired a burst of nitrogen gas to stir up material and trap it in a collection head. What happened next was not in the script. When TAG-SAM touched the surface, it did not stop. The surface of Bennu was so loosely packed, so low in cohesion and density, that the spacecraft's arm sank 48 to 50 centimeters into the asteroid before the contact sensor triggered the retraction sequence. Telemetry showed the surface behaving more like a liquid than a solid at the point of contact. One scientist described it as touching a pile of ball bearings with no friction between them. If OSIRIS-REx had lingered for more than a few more seconds, the thrusters keeping it stable might not have had enough force to pull it back out. The collection head captured far more material than the minimum mission requirement of 60 grams. So much material was collected that rocks jammed the seal of the sample container open, and fine particles began leaking into space. The mission team had to skip a planned mass measurement of the sample and move directly to sealing the capsule, accepting that some material was being lost, to preserve what remained. The final count after return to Earth, 121.6 grams, more than twice the minimum requirement. The sample canister was opened at NASA's Johnson Space Center in Houston on September 26, 2023, 2 days after landing. The initial images showed dark material coating every internal surface, fine-grained black dust that had escaped the collection head and settled throughout the capsule during the years of transit. The full scientific analysis took months and involved laboratories across the United States, Japan, Canada, France, and the United Kingdom. The results, published in a series of papers through 2023 and 2024, confirmed what the mission team had hoped and found several things they had not expected. The sample contains magnesium-sodium phosphate, a mineral that forms in liquid water. Its presence indicates that Bennu's parent body, a larger asteroid that broke apart billions of years ago and produced Bennu as a fragment, once contained liquid water. The water did not come from outside. It was produced internally, through chemical reactions between water ice and rock in the warm interior of the parent body. The phosphate crystals are the fossilized record of that ancient aqueous chemistry. The sample also contains hydrated silicates, clay minerals that form specifically in the presence of liquid water, at concentrations higher than in any previously analyzed carbonaceous meteorite. This means Bennu's parent body was not just briefly wet. It was wet enough, for long enough, to extensively alter the original rocky material into hydrated forms. The organic content is where the results become most significant. The sample contains amino acids, not complete amino acids in all cases, but the molecular precursors to them. It contains nucleobases, which are the molecular building blocks of RNA and DNA. It contains a broad suite of organic compounds including aliphatic hydrocarbons, aromatic compounds, and compounds with nitrogen and oxygen incorporated into carbon chains. The organic inventory is richer and more varied than in any meteorite sample previously studied. These are not signs of life on Bennu. They are signs of the chemistry that precedes life, the same chemistry that was delivered to early Earth by asteroids and comets in the first billion years of the solar system's history, before the first living cell formed. Whether that delivery was essential to life's origin on Earth, a contributing factor, or irrelevant is still debated. But the Bennu sample is the strongest direct evidence yet that the raw chemical ingredients are present in primitive asteroids and were present in the early solar system in quantities large enough to matter. The planetary defense angle is the most immediate. Bennu has a non-trivial probability of hitting Earth in 2018-22, and the OSIRIS-REx data has made its orbit the most precisely known of any potentially hazardous asteroid. The improved trajectory models actually increase the estimated impact probability slightly compared to pre-mission estimates. Not because Bennu is more dangerous than thought, but because better data eliminated scenarios where it definitely misses, leaving only the genuinely uncertain cases. The Yarkovsky effect is what makes long-term trajectory prediction difficult. Sunlight heats an asteroid's surface, and as the warm surface rotates away from the sun, it radiates that heat, essentially acting like a tiny thruster. Over decades and centuries, this thermal force accumulates into significant orbital drift. OSIRIS-REx measured Bennu's Yarkovsky acceleration directly, for the first time, giving trajectory models a real number instead of an estimated range. For 2182, it narrows the uncertainty, but it does not eliminate the impact window. The response options being studied for planetary defense depend on knowing exactly what an asteroid is made of. A rubble pile like Bennu, loosely held together by gravity with no significant internal cohesion, responds very differently to a kinetic impactor than a monolithic rock would. The DART mission tested kinetic impact deflection on a monolith. Bennu is not a monolith. The TAG event demonstrated that even a gentle touchdown sinks half a meter into the surface. A kinetic impactor might not transfer momentum efficiently. It might just bury itself in the loose material rather than deflecting the asteroid's course. The Bennu sample gives engineers material parameters, density, cohesion, composition, to model what a deflection attempt would actually do. The longer-term resource picture is equally significant. Bennu contains hydrated silicates, minerals that can be heated to release water. Water in space is not just for drinking, it is rocket propellant. Electrolysis splits it into hydrogen and oxygen, which are among the most efficient chemical propellants available. A near-Earth asteroid with water-bearing minerals is, in principle, a refueling station. The concentration of hydrated material in the Bennu sample suggests that carbonaceous asteroids as a class carry water in a form that is chemically accessible. The asteroid belt contains hundreds of thousands of similar objects. After releasing the sample capsule on September 24, 2023, the spacecraft, renamed OSIRIS-APEX, did not stop. It fired its engines and began a new trajectory toward a different asteroid, Apophis. Apophis is 370 meters in diameter, nearly as large as the Eiffel Tower is tall, and on April 13, 2029, it will pass Earth at a distance of approximately 32,000 kilometers. That is closer than the ring of geostationary satellites orbiting Earth. At that distance, Apophis will be visible to the naked eye, moving visibly across the sky over the course of a night. It is the closest approach of a sizable asteroid to Earth predicted in the next century. The 2029 flyby is not dangerous. The trajectory is well characterized, and Apophis will miss Earth by a comfortable margin. But the gravitational interaction during that flyby will reshape Apophis's orbit in ways that are not fully calculable in advance, because they depend on how mass is distributed inside the asteroid, information that does not yet exist. OSIRIS-APEX will arrive at Apophis in April 2029, just weeks before the Earth flyby, and will observe the asteroid before, during, and after the close encounter. The plan includes a tag-style approach, descending close to the surface and firing thruster gas to stir up material for observation without necessarily collecting a sample. The goal is to characterize Apophis in detail before its orbit is altered by Earth's gravity, and to track the changes the flyby causes in real time. This makes OSIRIS-APEX one of the most valuable planetary defense observation opportunities ever arranged. An asteroid large enough to cause regional devastation if it hit Earth is about to have its trajectory altered by Earth's own gravity, and a spacecraft that spent years studying a comparable asteroid will be there to watch it happen. The origin of the organic molecules in the Bennu sample is not fully resolved. The compounds identified are consistent with formation through abiotic chemistry, reactions between simple molecules like carbon monoxide, ammonia, and water under radiation and heat. But ruling out contamination from Earth's atmosphere during the capsule's descent or from handling during processing requires extensive controls that take time. The scientific consensus that the organics are genuinely extraterrestrial is strong, but characterizing the full molecular inventory and its implications for origin of life chemistry is ongoing work that will take years. The water history of Bennu's parent body is also incompletely understood. The hydrated minerals indicate an aqueous phase, but how long that phase lasted, at what temperatures, and under what pressure conditions are all model dependent. Different scenarios produce different predictions for what minerals should be present and in what ratios. Matching the Bennu sample's mineral inventory to a specific parent body history requires laboratory experiments that replicate those conditions, work that is actively underway. Bennu's internal structure remains largely unknown. The surface behavior during TAG suggests extremely low cohesion, but whether that low cohesion extends throughout the interior or whether there is a denser, more consolidated core is not measurable from surface observations alone. This matters for impact modeling and for understanding how rubble pile asteroids form and evolve. And the 2182 impact question will not be definitively resolved for decades. Continued radar and optical tracking of Bennu, combined with the improved orbital model from OSIRIS-REx, will progressively narrow the uncertainty. At some point, the window will either include or exclude a definitive impact trajectory. The current estimate is 1 in 2,700, low enough to not be an immediate concern, significant enough to stay on the monitoring list for the next 160 years. A spacecraft launched in 2016 spent 4 years traveling to and orbiting an asteroid the size of a skyscraper, pressed a robotic arm into a surface that almost swallowed it, collected material that formed before Earth existed, and dropped it in the Utah desert in a capsule that landed within 300 meters of its target coordinates after a 7-year journey. The material inside contained the molecular building blocks of life, water that had been locked inside rock since the solar system's first million years. Organic chemistry, complex enough to make planetary scientists call it, carefully, some of the most significant extraterrestrial material ever studied. The asteroid it came from might hit Earth in 2018-22. The spacecraft that collected the sample is now flying toward a different asteroid that will pass closer to Earth than most satellites in 2029, there to watch what happens when Earth's gravity reshapes a potentially hazardous object's path. The mission that was supposed to answer questions about asteroid chemistry turned into something larger, a direct investigation of where Earth's ingredients came from, and a first real test of whether we understand the trajectories of the rocks that could one day threaten to return them.